analysis is a method used in analytical chemistry to find out how much of a substance is in a solution. It usually involves titration, where we add a solution of non-concentration into other solution until the chemical reaction is complete. This is very important when we want to measure accurately, like in water testing. Now, why is this technique important in water treatment? Clean water is something we use every day for drinking, cooking, and even agriculture. But untreated water may contain harmful substances like chlorine, heavy metals, or high mineral content. Volumetric analysis help us to measure these things so water can be treated properly and made safe to use. This method is commonly used to check water hardness, which is caused by calcium and magnesium ions, chlorine levels to ensure they are not too high or too low, and acidity or alkalinity to make sure the water is balanced. Without proper testing, the water might look clean, but it could be dangerous to our health. So, let's get started and learn how chemistry helps protect our water and health every single day.
Now, I will talk about the theory of volumetric analysis in water treatment. First, what is volumetric analysis? Volumetric analysis is a laboratory technique used to determine the concentrations of an unknown solution by reacting it with a solution of known concentration. Volumetric analysis commonly involves a set acid-base titration where an acid or base is gradually added to a solution until the reaction reaches its endpoint, typically indicated by a color change. Why it's used in water treatment? In water treatment, volumetric analysis is primarily used to measure the pH levels of water, which is essential for maintaining water quality. Titration helps determine the amount of acid or base needed to adjust the water's pH to the required level. Next, role in water quality control. Titrations ensure that water is neither too acidic nor too alkaline, both of which can be harmful to human health and industrial equipment. By adjusting the pH, treatment plants can optimize the effectiveness of chemicals like chlorine or for disinfection. Lastly, the benefits of acid-base titration in water treatment. First, help calculate the precise amount of chemicals required to neutralize the water. Next, prevents corrosions in pipes and other infrastructure. Ensure safety by neutralizing harmful contaminant, making water safer for consumption and use in industrial processes.
In this section of our presentation, I will demonstrate how acid-base titration, a key technique in volumetric analysis, is applied in the water treatment industry to monitor and control water quality. The methodology typically involves in the following steps. First, sample collection. Water samples are collected from various stages of the treatment process, such as raw water intake, post-treatment output, or during distribution to analyze parameters like pH and chemical content. Secondly, preparation of reagents. A standard titration solution is prepared, commonly a strong acid, example HCl, or strong base, example NaOH, depending on the specific analyte being measured. Indicators like phenolphthalein or methyl orange are selected based on the expected pH range of the endpoint. Number 3. Acid-base titration process. The collected water sample is titrated against the prepared standard solution. If measuring alkalinity, a a known volume of the water sample is titrated with a strong acid, example HCl. If measuring acidity, a strong base is used, while the titration continues until a color change is observed, signaling the equivalence point. Here is an example of a simplified lab procedure. Firstly, a known volume of the water sample is placed into a conical flask. Secondly, the indicator is added to the sample. Next, the titrant, acid or base, is slowly added from a burette while swirling the flask until a color change indicates at the end point. In this experiment, a white tile is required to observe color change clearly. And lastly, the volume of titrant used is measured. Number 4. Titration curve visualization. To enhance understanding, we will include a titration curve graph plotting pH versus volume of titrant added. This curve helps visualize the buffering region, the sharp pH change near the equivalence point, how the choice of indicator align with the steepest slope of the curve. Number 5. Calculation and interpretation. Using the formula C1V1 equals to C2V2 to calculate the concentration of acid or base in the water sample. This data is crucial for adjusting pH levels to meet regulatory standards, ensuring safe water for industrial or human consumption, optimizing chemical dosing in the treatment process. Number 6. Real-world application in industry. In large-scale water treatment facilities, automated titrators and pH sensors are often used. Results from titration inform the dosing of lime, alum, chlorine, or other neutralizing agents, and ensuring pH remains within a target range, typically 6.5 to 8.5 for drinking water.
In this analysis, we assessed the concentration of several key contaminants in the water sample. By performing volumetric titration, we were able to precisely measure the levels of chlorine, iron, ammonia, and nitrate. The titration procedure involved carefully adding a standard solution to a known volume of water until the reaction reached its endpoint, indicated by a color change. Here are the key findings. The first one is chlorine, Cl negative. The concentration of chlorine in the sample was found to be 15.3 mg per liter, which is within the acceptable range for drinking water as per safety standards. Iron Fe2+, the iron concentration was measured at 18.7 mg per liter. This level exceeds the recommended limit for drinking water, suggesting possible contamination that needs attention. Ammonia NH3, the ammonia concentration was relatively low, recorded at 6.8 mg per liter, indicating minimal contamination from organic sources. And the last one is nitrate, NO3 negative. The nitrate levels were also found to be low at 5.6 mg per liter, which is acceptable for drinking water. The titration curve represents the relationship between the volume of titrant added on the x-axis and the pH of the solution y-axis during a titration process. Before the equivalence point, the initial part of the curve, the pH increases slowly as the titrant is added, reflecting the gradual neutralization of the acid or base in the solution. At the equivalence point, the amount of titrant added completely neutralized the acid or base in the solution. This is marked by a sharp rise in the pH, which is a characteristic feature of the titration curve. In this example, the equivalence point occurs around 30 ml of titrant, where the pH reaches 7, indicating a neutral solution. After the equivalence point, the curve rises steeply as the titrant continues to be added, indicating that excess titrant is now present in the solution. The pH continues to increase, but the rate of change slows down after the equivalence point. This sharp increase in pH around the equivalence point is a hallmark of acid-base titrations, where the exact neutralization of the acid and base results in a clear shift in pH. The red dashed line indicates the equivalence point, and the label mark shows the pH values at this critical point in the titration process. These results highlight the importance of regular water testing to ensure water quality. While some contaminants are within safe limits, the elevated iron levels indicate a need for further treatment or filtration. The overall water quality appears acceptable, but attention should be given to areas with higher iron concentration to ensure safety for consumption.
In conclusion, today's presentation has demonstrated the critical role that volumetric analysis plays in ensuring safe, clean water for our communities and industries. Through the systematic processes we've outlined, from sample collection to titration and calculation, we can see how this method provides precise, reliable measurements essential for water quality control. The titration curve visualization shows us exactly when neutralization occurs, giving us confidence in our measurements. Our example results illustrate real-world applications. While chlorine levels of 15.3 mg per liter and low ammonia concentrations indicate proper treatment, the elevated iron levels at 18.7 mg per liter remind us why continuous monitoring is crucial for identifying potential contamination. Every day, water treatment plants worldwide rely on volumetric analysis to make critical decisions about chemical dosing and pH adjustment. Without these precise measurements, we couldn't maintain the safe pH range of 6.5 to 8.5 for drinking water or optimize disinfection processes. The beauty of volumetric analysis lies in its simplicity and reliability. This technique bridges the gap between basic chemistry principles and life-saving applications, ensuring that clean, safe water remains accessible to all.